Welcome to Breadboarding. This is video 16 in the Breadboard 8088 PC series, and this is the fourth video looking at the Monochrome Display Adaptor video controller. So this is part of our plan to build a basic floppy disk PC capable of booting MS-DOS. Then we're going to be going on to see if we then run an early version of Windows. In the previous video, we've done some changes to the main board to make it use IO addresses rather than memory mapped IO. We also updated the monitor and we added the first couple of chips to the video controller board, and we just need to do a few tests on this before we go a little bit further, and then going to talk about what bits we're going to add after that. So we're going to add the video RAM, the cathode ray tube controller and the video digital analog converter and the output VGA connector, and this should allow us to do some basic testing to initialize the CRTC, the video DAC, and to get some basic video output. So this is what we did last time. We had the IO port decoder, the clock PLD, which is taking the 25 megahertz oscillator dot clock, and that will be dividing it down. And what we'll then be doing is adding the cathode ray tube controller. This will then be feeding the horizontal sync, vertical sync and display enable signals up further on down the line. We'll then be driving this off a character clock, which is going to be the dot clock divided by 8. And then we'll be adding the video RAM. So this is a dual port video RAM, hooking that up to both the CRTC and the main system address and data bus. And this will also be driven by the dot clock divided by 4 to switch between the character byte value and the attribute byte value for each CRTC address. We need to switch the RAM between the odd and even byte. Then we'll add the video digital analog converter. We'll wire up the display enable, horizontal sync, vertical sync, and then what we will do is to set the input pins on the digital analog converter probably to some of the output address lines from the CRTC, and this will just mean we'll get some sort of multicolored test pattern on the display just for getting some testing. We're going to be making use of the various addresses here. The items blacked out there are the control and status registers that we'll be adding in later stages. So let's have a look at testing the IO port decoder first. The easiest way to do this was actually just to pull the chip out and put it in the programmer, and I have done some tests for this particular device. So let's have a look at the PLD definition first. So this is the MDA video controller IO port decoder, and what this does is decodes the IO addresses for the Monochrome Display Adaptor. So we've got the video digital analog converter palette for the first 4 addresses. Now that isn't a standard MDA adapter, but we're making use of some of the unused ports there to add our VGA compatible palette here. Then we've got the cathode ray tube controller address or index, and then the cathode ray tube controller data. And then you can see here the CRT status port and control port are the things that we're not doing as part of this one. So we've got quite a few input lines here, and really it was a lot easier to test this using the test rules in the XG Pro programmer. And so we've got all these input lines, the IO read, IO write, the signal that we added to the main decoder, which tells us when all the top address lines are 0. And then we've got the various outputs here. And in our rules down here, all I've done is added the sort of binary values on here, just makes it a bit easier to work out the tests. So we've got the palette read, palette write, the general 6845 chip select, CRT control and the CRT status. So if you have a look at XG Pro, so I've loaded in the IO decoder here. We just read that just to make sure it's installed properly. And then I've used the test facility here to define some rules here. So we've got all the rules here for the pins, and I've put in a lot of the main rules here, making sure that the I19 to I12 line is being taken into account of the IO read and IO write and all the various address line combinations. And basically when we do the test here, it passes. And I had one mistake that I'd found, that I'd missed out one condition. So this actually picked up one mistake in doing this. So I corrected that condition. So that should be okay. So if you now take a look at the clock PLD, this will be a little more difficult to test using rules in XG Pro. So I think this we may very well find it just easier to hook up to the dot clock and look at some of the output signals here. There's one of the signals here, the underline row address. We probably need to connect this up to the CRTC to test this. So I don't think we need to do any rules for testing this particular one. Timing here is the same as what I did for the original Nanocomp 6809 VGA controller. So these rules and things should be okay. And similarly, the character latch, the shift register latch and the attribute latch signals should be the same as what we needed from the previous project, but we might need to review these if we don't have things coming out quite right. Let's take a look at the board as it is at the moment before we start testing. So you can see on the top right, this is the IO decoder, which you've kind of tested already in the EPROM programmer test facility. And this is the clock, 25 megahertz clock, the output from the clock going into the PLD, and then all the signals on the left hand side here are largely coming from the clock. There are a couple of one of the outputs is to do with the underlying row address, and so what I have done here is wired up the RA0 is to 0 volts and all the others are wired up to 1. So I think it was row address 14 where the underline was going to come. So at the moment I've just wired that up, so we would expect that to be 1 or high at the moment, and then perhaps if we hook this line up to something that toggles between 1 and 0, then we should see this line toggle, and when we eventually wire this up to the CRTC, then we should see the underline row address to go high when we get to row 14. So I've got my oscilloscope probes down here, so what I'm just going to do is to hook up the probe to the clock circuit, and what we'll do is have a look at the oscilloscope output on the PC, and all I'll do is just show a couple of the signals coming from various points in the circuit. So here's the output from the oscilloscope, and we can see that at the moment this is on the oscillator output, and if you look down the bottom right hand side here, you can see this is 25.180 megahertz. The peak to peak is just over 5 volts, it's about 6.16 volts, but you can see that's largely due to the capacitance on the board causing overshoot and undershoot. So then if we move this on to the input, so this is the input to the PLD, which is almost the same. So let's take a look at some of the other signals now. So if we go, probably the first one we'll be looking at is the dot clock output. So we have two outputs down here, and I'll wire up both the oscilloscope probes here. So we've got the buffered dot clock and the inverted dot clock. Now I'm not 100% sure I need the inverted dot clock, but it's useful to have it should we need it. So you can see here that we've got the same frequency clock, but one of the signals is inverted. And you can see there's a little bit of bouncing around here, but the signal's relatively clean and we should get fairly good logic levels. So if we leave the upper one on the dot clock, then if we look at the QA, which should be the dot clock divided by 2. So we have the dot clock divided by 2. And then if we look at the dot clock divided by 4, okay, so we now see the dot clock divided by 4. And then if we then go to the QC, which is the character clock, so this we can now see that the character clock should be 4. There's a little bit of a problem with it synchronizing. I might just swap the probes around. So the oscilloscope was having trouble syncing with the other signal there. But what we can see here, this is our character clock. So this should be a 3.1 megahertz clock. So that is the character clock that the CRTC will be using. And we can see here that we've got 1, 2, 3, 4, 5, 6, 7, 8 dot clock cycles per character clock. So it looks like those clock signals are coming out okay. There is an inverted character clock as well, which the original MDA design did actually feed an inverted character clock into the CRTC. You can see there that that is the inverted character clock. So we've got that should we need it, and I guess what that will do is effectively shift all the signals along by half a clock cycle. So this is the character clock, and what I'm now going to do is to look at the character latch. So the character latch, you can see here that this actually goes from low to high somewhere around just before the halfway mark. So it's going between second and third clock cycle. So if we think that the 0 is the first one, then 1, 2 and 3, and then 4 will be this one, then 7 will be the clock cycle just before this. So this should be around the end of 2 to the end of 3. Now if we look at the shift register latch, that should be a little bit later. And you can see the shift register latch is some way halfway in the middle of this one here. And this is the reason, is because we actually need the character latch to find the character value in the video RAM and send that out to the character ROM, and then the character ROM then needs to provide the output to the shift register. So that's why we need to have a bit of a gap between this to allow the signals to go from the video RAM through to the character ROM and then out to the shift register. And at the moment, I think the attribute latch should be around the same time. We might need at some point in time to change the attribute latch to perhaps be slightly different, but those signals look like they're pretty reasonable at the moment. And then if we finally look at the underline, so this is the underline output at the moment, you can see that's just high because we've hard coded it to row 14, and all I'm going to do now is to plug this into the character. So this is now plugged into the character clock QC, so you can now see that that will vary with that as well. So it looks like all of the signals there are correct, and so what we can now do is to start to look to wire up the other parts of the circuit. So let's unplug the oscilloscope leads and some of the test wires that we put in for doing our bit of testing. So the reset line will need to be wired up because the counter won't count if we don't have the reset line in there. And so, right, okay, I've undone all that. So we're just going to put all the chips in. So this is the video RAM, and it's just going to squeeze in here. A lot of the lines from the buses are going to come in on this side, and then we're going to feed them over to other parts. So we're going to need to leave slightly more holes on that side, I think, for the moment. Then the CRTC, a lot of the address lines here are going to be wired up to here. Again, for the CRTC, we need to make sure that the A1 line is lined up with the MA0 line. And again, we probably want to have more space on the left-hand side because most of these are just going to be wired straight across here. Can plug that in there. And then this is the pallet chip. And again, this probably needs to have 2 lines on that side. No, let's leave it with 3 lines on that side, I think. And then here we go. So this is the KiCad diagram. What I'm going to do is to wire these up, and I'll reference back to the KiCad diagram as we go through. And what I will do is to print out a version of this at some point in time, and I'll check it all off. But for the moment, I'm just going to refer during this video to look at each of these whilst we wire them up. But I won't be checking anything off yet because we're going to be wiring up various things like these inputs to the digital analog converter. We're just going to wire up temporarily to the CRTC address outputs here, and what this will do is once the palette has some different colors loaded, then it should mean that we should see the different colors. We're going to need to wire up the connector here with all these various resistors and the current source here, and once that's all wired up, then we should be able to get some video signals out of this. Okay, so I've just soldered in the pins to the VGA connector. Just to be careful, there's an extra pin at the top there, 16, which is ground. And we're just going to wire up these. So we've got the red, green, blue video signals, then there's a lot of ground signals. And then there's a 5 volt with a resistor there to stop the monitor draining all the power from this board. Then the horizontal sync and vertical sync. We just need to wire in the ground rails there. Now we also now need to add the 75 ohm resistors to ground on the outputs there. And then we're now going to wire in the red, green, blue signals. Now we need to do the constant current source. And the constant current source discussed in the video in the nanocomp series and the calculations for this, it needs a 15 ohm resistor to vary the current. And what I've done is put a small variable potentiometer in there, and this will be nominally 15 ohms, but we can tweak it a little to increase the intensity. Wire in the dot clock, and now we need to just put the write enable and read enable signals, and the A0 and A1 address lines, which we're going to wire up to the top there a little bit later. So now we're going to connect the CRTC memory address lines to the left-hand side of the video RAM. The video RAM is always going to be read and always enabled on this side. So now we're going to put in the chip enable, the address 0, the character clock, and the E signal and the read-write signals. Just a little confusion there which way around to do it. And there's a reset there as well. Okay, so just check those. So now we're going to wire up the raster row address lines up to the PLD there. Just a temporary measure for the moment. Now we do need to temporarily put an inverter in for the display enable to go into the blank input to the video DAC. This will come from a PLD on the left hand side a bit later. Then we're wiring in vertical sync and horizontal sync. Horizontal sync also needs to be inverted as well. Put in a power distribution bar. Now we're going to wire in the data lines to the main processor board and the address lines. Then we're going to take the address lines up to the IO decoder. That's the A0 to A7 and then the top address lines as well. And now we're going to need to wire in the data lines to the CRTC and also to the video DAC. Just check those as well. Okay, so that's the board pretty much wired up. All we're going to need to do is to wire these various fly leads into the main computer board onto the bus rails and things, but we should have enough now that we can plug in a VGA monitor here and get some sort of signals coming out. We're going to need to feed into the video DAC some signals which I'll probably derive from some of the memory address lines down here, and it just means that every couple of characters the colours will change. So I'm going to break the video now. So in this video we've tested the clock and the IO decoder, we've managed to install the video RAM, cathode ray tube controller chip and the video digital analog converter, and also all the connections we need for our VGA connector. Didn't have quite enough time to do the test software and to do a bit of testing. So in the next video we'll be looking at testing this and writing the software to initialize the cathode ray tube controller and the video DAC, and if we have time there we'll also go on to install the character latch and character generator shift register. So thanks for watching. If you don't want to miss out on future videos, please hit subscribe, and if you can hit like, it just helps to make the videos available to a wide number of people. Thanks for watching.